Hello everyone, welcome back again. Today we'll look at another example of basic electrical engineering and see how we're gonna solve it using our knowledge we've learned from this course. So this is our circuit. So if you look carefully, you see that the two sources, the current source and the voltage source, are in this specific form, the phasor form. So you can just say that this is a sinusoidal steady state analysis. So we have to use that knowledge to find Ix over here. So let's see how we're gonna apply it. So in the first part, let's identify what is given to us. So as we can see here, the angular frequency is given as 5 radians per second. As you can see, 5t. And the next part, if you look here, the current source, write them down in the form of a frequency domain with angle of 75 m. Sorry for this mistake here. And we have a voltage source over here, which is 2 angular to 67 voltage, excuse me. And then we have to convert these two, the capacitor and the inductor, into an imaginary form, which will be easier to calculate later on. So the capacitor, we use this formula again, 1 over J times the angular frequency 5, and then the 6.6 farad, and the answer will be minus J 0.33 ohm. Next thing, the inductor, we use again the formula. If you don't remember, it is J J times angular frequency again 5, and then 6 Henry. You get J 30 ohm. So after we've identified the given, we have to see what theorem we can use or analysis we can use. So if you use mesh or nodal analysis, this would be very difficult, and also goes to the Thevenin and Northern theorem. So the best option here would be to apply the superposition theorem. So firstly, you can choose whether to ignore the current source first or the voltage source first. For this example, I chose to ignore the current source first. As you can see here, you can just cross out the current source. It will become an open circuit. So you can see here terminal 21, and the voltage source is still there. In this, because there are no other resistor, capacitor and inductor, we can just ignore the parts of above and the bottom and focus on this voltage part over here. Okay, now we've only looked at this part after we cancelled out the current source. So as you can see here, we want to find Ix over here, which is, now we've labeled it as I voltage. It just because this circuit will be impacted only by the voltage source and the other materials in this area. So if you look carefully, firstly let's find the equivalent circuit to this circuit we have right now, because this is quite difficult to solve from using this particular diagram. So let's just find a way to make it much clearer and easier. So if you look carefully, this capacitor and this resistor are in series. The same goes to this 2 ohm resistor and this inductor. So we have to use the formula that we already know. So if they are in series, just add them together. You get these to equivalent circuit. So as you can see here, we got Z1 and Z2 over here, and then this C1 and C2 is in parallel with each other. So again, apply the normal formula, and then you get this particular number, which now you can find current that is coming out of this voltage source. It is advisable you just convert this voltage source into this imaginary form first, so it will be easier for you to find the current, because it will be much more convenient to convert them into the same forms. So as you can see here, the final answer is down there. So after we've done with the voltage part, now we focus on the current part. In this part, you can just here ignore the voltage source and focus on the current source. Here, look, it will become a short circuit, and instead we are focusing on Ix over here. So you can name this I current and concentrate on finding it. So how do we find I current over here? As you can see, the circuits are in a mess, and it's a little bit difficult to find the Ix over here. So once again, we name this part I current, and what we can do if we are focusing on finding this part of I current, we can apply nodal analysis for this node over here, and we can find it by finding the voltage passing through this capacitor and this resistor. And then what we've known is the last part, these two were in series, as well as these two, but now there is no source here, so these two are in parallel and these two are also in parallel. But we the voltage passing through these two are the same, and that goes to this bottom part too. So we want to obtain this and this, we can combine this together and then find the voltage source passing through it. So we combine the first part into Z1 and combine the top part into Z1 and the bottom part into Z2. We'll get this equivalent circuit, and then we find the voltage across the two Z's. The first Z, you can use the normal formula. You have to convert this into the imaginary form first, so it will be easier to find and calculate in your calculator. So use the normal formula here, I times the C, I times R, which we can use the C over here, and you get two answers. And then we can now apply the nodal analysis on this particular node, which will be KCL on this node. So there is a current passing through here into the node, and then I current coming out of the node over here, exactly the same, and then another current coming out of the node into the resistor. So we can write the equation minus I of minus J 0.33 ohm capacitor here, plus with I current, and then plus again with I of the current of 2 ohm resistor over here. And if you move things around, we finally have I current. Now we can just plug in the values, but first we have to find these two first. So for the current moving through here, we have already found the voltage source, the voltage passing through earlier. If you forgot, you can just go back um, a few minutes earlier and use normal formula. V over R, you get I that passes through here, and then the same goes to this. We already obtained the voltage passing through, so use the formula, and once that, you can plug these two numbers into the equation that we've already identified, and you get I current, which completes our second part of this equation, of this solution. So now we can complete our final answer. So using the superposition theorem, you have to add the two numbers that we already obtained, which one belongs to when we consider only the voltage source, and the other one when we consider only the current source. We add them, and since this is sinusoidal steady state analysis, we have to convert this back into this form over here, the time domain form, and you can use the r cos theta and the r sin theta properties, which if you've done it correctly, you get these numbers 0.096 with a degree to 67.47 degree amp, and you will convert it into its final proper form, which is the answer below. So that completes our solution for this particular equation, a problem for the sinusoidal steady state analysis. Thank you very much for watching.